for the last few minutes, we're going to talk about some nomenclature and directing effects. But we got to go through the nomenclature first so you'll understand the directing effects. Right. So with the benzene ring, if it's unsubstituted, there's no impediment to addition to that ring. And also naming wise, you name it based on the substituent that's on there, right? So let's say for this reaction, for this product right here, this would just be bromo benzene, right? This would just be tert-butyl benzene, right? No problems, no numbers, no anything. If the ring is already substituted, like here, right? Anything you add to that ring is going to have to occupy one of three positions, right? So we don't, when it's when it's mono-substituted, like the first case right here, and then we add another group, now this becomes a di-substituted system. Because now I have two substituents on the ring, here and here. If it's di-substituted, the convention for naming it changes. You don't use numbers. So for di-substituted benzene rings, no numbers are used when you name it. Right? No numbers. It's only positions. So now I'm going to use numbers to explain it, so to make it make sense. All right. So we're going to start here. Wherever that position is going to be 1. This is 2, 3, 4, 5, and 6, like that. All right. So if it's at the 2 position, which is immediately adjacent to the group that's already there, we call that the ortho position. All right. This is important because when we talk about reacting a substituted benzene ring with some electrophile, when that reaction happens, it can only happen at one of these 3 sites, either ortho, meta, or para. Right. So here, if it's at 1, 2, but we don't call it 1, 2, we call it ortho. If it's at position 3, you can see that right here. This is 1, 2, 3, like that. Then we call that the meta position, or 1, 3 di-substituted. And then if it's here like this, right, then that's 1, 4, and we call that para. So for di-substituted benzenes, you do not use numbers when naming them, right? You only use the positions. And if you look at it this way, if you go the other way, I know somebody's thinking this, what if I go the opposite direction? It's still the same. If that X group is out here, like that, it's still ortho. It's just on the other side. You would just go around the ring the other direction. And it's the same for meta and for para. All right. The reason I'm saying that is because those positions are important when you think about how benzene reacts with other things. Right. So these down here are just some common names, right? Anisole. Anisole is this part of the ring right here. That's anisole. So anisole is really methoxybenzene. Right. But if I stick a group on there, like a chlorine, look at the name now. The name is now chloroanisole, because anisole is the common name for methoxybenzene. So we use that. We use that name when you see the term or yeah, the word anisole is telling you that it is a benzene ring with a methoxy group attached to it, like that. That's terrible. Right? There are a lot of common aromatics with common names like that: anisole, aniline, and other compound, phenol, other compounds like that. Right? I'll give you a couple of other examples too. Right? But notice the prefix orthochloroanisole. So it's ortho because chlorine is at position number 2, adjacent to the methoxy group. Chloro because it's a chlorine, and anisole because of the methoxybenzene system that chlorine is attached to. All right. If we look at the other, you can see immediately this is meta because your methoxy group is here, and then your chlorine is here, right? And that has a 1-3 arrangement. So this is 1, 2, 3 like that, but we don't use numbers. For disubstituted systems, we use positions. So it's either ortho, meta, or para. So metachloroanisole, same thing. The anisole is the methoxy benzene ring. The chlorine is the substituent. And so we call it metachloroanisole. And then the other one is para. Need to fix that because that's not a chlorine. Let's white it out. I love this app when it's working. Right. So this, and then I need to white the bottom part out too. Right. So what if this was anisole? I'm going to put the methoxy group here. Right. So that would be parachloroanisole. There are other aromatic compounds with common names like that. One of them that is highly used all the time is aniline. Right. Aniline is actually used as a solvent in a lot of cases for certain reactions. Notorious for being able to for getting rid of it. It just has a really high boiling point. Kind of sucks to use it, but sometimes you can't avoid it. Another one is here. This is toluene. Right. So toluene is another example of a monosubstituted benzene that has a common name. So you wouldn't call that methylbenzene, even though that's the proper name for it. You call it toluene. All right. So what happens if I take aniline put bromine there? How would you name that? What's the arrangement between the aniline part, which is this, right? That's the aniline part. What's the arrangement between the nitrogen and aniline and the bromine?
Is it in the second position?
So this is one that would be that second would be there.
Oh,
3
third.
So what's the term we use for that 1-3 arrangement?
Meta.
Meta. Good. So this would be meta, and then bromo, aniline. All right. That's because again, aniline is a common name, and when we have a common name, we use that. Let's do another one. Let's do put this on a different page. What about this one? You can see the common name for this is what?
Tule,
Okay, toluene, good. We'll take it.
toluene.
Yeah, you're good. What's the arrangement between the methyl and the chloro? Position
Is in the
wise.
fourth position.
1-4. 1, 2, 3, 4. If it's 1-4, we call it para. So this is what's the terminology for this?
Para chloro toluene.
Yeah, you're right. Parachlorotoluene. No, and you could also abbreviate the position with the first letter. So para can be P, ortho is O, meta is M. Let me show you another one. And I hate squeezing this in here. This is not good. Maybe I'll rewrite it after class. This is another common name, aromatic. This is phenol. Right. So phenol, it will follow the same convention. You stick a group on that ring. Right. This is the phenol group, and then the iodine is attached to that. So how will we name that? What's the relationship between the OH and the iodine?
So 1 second, 1 second, 1, 2.
It's 1, 2, right? So that is what?
Ortho.
So this would be ortho or O, iodo, phenol. Right, the iodo part is for the iodine. All right, so when we think about the reason why this is important is because now we're going to talk for a few minutes before we leave about reactions of substituted benzene rings. So that's this section right here. So let me cut this out because I don't want to try to squeeze all this information in this little box. Let's see. There we go. I'll put it on this page right here. All right. So this is important because depending on what's on the ring before the reaction, that's going to actually determine what the reaction, how the reaction happens. Right. So for this ring right here, just make that. For this ring right here, we have a methoxy group attached to it already. Right. So this is anisole. Right. And because of that methoxy group, when you have a group on the ring experiences what we call directing effects. And depending on the nature of the substituent, that's going to determine how it directs traffic, where the incoming electrophile can go, because we're still talking about electrophilic aromatic substitution. So if this is a donor, and I have it down here in the box, but I feel like I still need to explain it. So if this is a donor, by donor, I mean electron donor, right? And you can see the methoxy can donate electrons into the ring by resonance. So it is indeed a donor. Right? It can be resonance or induction. Doesn't matter if it can donate electrons or electron density into that ring, it's going to act as a donor. And if it's a donor, then it's going to be what we call an ortho-para director. So we can kind of think of a little acronym. If it's a donor, it's orthopara. So donor is an orthopara director. Any donor is going to be an orthopara director. And by donor, again, we mean donating electrons. So for this reaction, we know we're going to put bromine on the ring, right? We know that by now because this is a halogenation. Bromine plus an aromatic ring in the presence of iron 3 bromide is a halogenation. So when we look at the two products, notice the bromine is at here and it's here, which is a 1-4 relationship. And I'll explain the mechanism. I'm not gonna have time to do it today, but we'll go through that on Friday. I think it's in that aromatics video though, if I'm not mistaken. Right, so you got a 1-4 relationship here. And between here and here, you have a 1-2 relationship. So donors are orthopara directors in electrophilic aromatic substitution. Right, that's really important because it's the opposite for nucleophilic aromatic substitution. Like if I was adding a nucleophile to the ring, a donor would have the opposite effect. But for electrophilic aromatic substitution, I'll just abbreviate substitution. Right, if I have a donor on the ring prior to the reaction, it's going to be an orthopara director. So it's going to direct traffic. And we say that the donor is activating. Right, it activates the orthopara position. I'll show you that. And it's really based on resonance, but I don't want to start it and then run out of time. But a donor on the ring is going to activate the orthopara positions for electrophilic substitution. So it's going to make them able. Go ahead.
Sorry, go ahead.
Go ahead.
What do you mean by activate?
So do you see the first resonance arrows I drew right here?
Mhm.
Let me draw the resonance form for that, right? So the resonance form will look like, and I'm just drawing it on this side because I don't have room on the other side. It will look like this. So this is OCH3. That's positive. You got a pair of electrons here. That's negative. And then you have a pair of electrons. I'm a pi here. You see that? So at that site right there, I can add an electrophile because there's a pair of electrons there. So that site is activated.
Because you added a pair of electrons.
Remember, if I'm adding an electrophile, I need a nucleophile to react with it. And I need something that's going to give it a pair of electrons. So if I draw the resonance form, this is how the donors activate these positions. If I would draw the resonance form and get a pair of electrons at that site, what site is that relative to the donor?
Ortho.
It's ortho. Right, so that site is activated. So this is, I'll just say the ortho site is activated. Right, by resonance. Now, what can I do another resonance form for this?
Yes.
I can do this, can't I? I can push this pair of electrons here and this pair here. And then that's going to give me, and I hate to squeeze this in here, but that's okay. We're going to make it work. It's going to give me this, and I'll fix this before I post it. It's going to give me that. Is that right?
Mm-hmm.
And then that and this. Right, so now you can see the parasite is activated.
Mm-hmm.
Right, so now if I add an electrophile, that's where it's going. It's got to go either ortho or para. It can't go anywhere else. That's why we say donors are orthopara directors, because they activate the ortho site by putting a pair of electrons there or concentrating electron density there. And then by the same token, they also activate the parasite. All right.
I have a question.
Go ahead.
Can you go back to that second resonance that you just drew with the para side on?
Mhm.
Why can you do another resonance with the para?
Oh, you
on the
can.
top line?
You can
Oh,
to activate the other ortho site.
oh,
Yeah.
so
you
it
can.
wouldn't be what's it called? The sixth site? It wouldn't be that?
Yes, but it's still ortho because it would be right here. The electrons will end up here, and they're still adjacent to that group. If that makes sense, right? If I have a substituted ring like this, whether it's here or here, it's still, that's why we don't use numbers. Because you
Oh.
use the 6 and said, oh, what about 6? It's ortho. Either side is ortho. Does that
Oh.
make sense?
Mm-hmm.
Yeah, and the same thing here. That's parallel. So this is ortho, that's ortho, and that's para. That's why we're not using numbers right now. But you're right. I could draw this resonance form like that and like that and put a pair of electrons there, but it's still going to be considered ortho because it's right next door to the initial substituent.
Okay, so ortho is either 1, 2, or 1, 6.
Yes,
Okay.
you can think about it like that. Yep. All right. That's a great question. Thank you for asking that. We'll talk more in detail about that on Friday. I think it's in the aromatics video that I sent, but I can't remember. So if you haven't watched that, watch it. And then I'm not talking to you, Tia, by the way. I'm just talking in general. If you haven't watched that video, you should watch it because all this information is just going to get reinforced if you do. All right. If not, read the section in the chapter on aromatics, look at the syllabus, see where that section is and find it. But you got to do something. All right. We're going to stop right here.